Hello everyone, this is our paper with a title Adaptive Circuit Power Control for Downlink Massive MIMO Systems. I'm Shanko Chura from Harasa University, Dr. Alam Nagash, and Dr. Heno Wende from Addis Ababa Institute of Technology, Dr. Faisal Dabo, Professor Raja Verappa, and Maile Takalo from Adama Science and Technology University. These are the outlines of our topics, the background of massive MIMO systems and those radio frequency chain components, why we are motivated to work on this area, the objectives to be achieved, some state of the art and literature surveys, the methodologies through which we can achieve those desired objectives. And again, we'll be dealing with how those radio frequency chain components can be energy and spectral efficient. And finally, we'll be discussing the results and draw the conclusion. Before stepping to our main work, which is how those radio frequency chain components are energy efficient and power efficient, we'll consider the three modalities of MIMO systems. In the first case, a MIMO system in which a single base station can have a number of antennas, and the same number of antennas can be installed on a single terminal. That means the number of antennas on a single user should be the same to the number of antennas to be installed on a single base station. And again, the number of antennas, the number of base stations are also the same to the number of user terminals at the uplink. In the case of multi-user MIMO systems, a number of antennas still can be installed on a single base station, and those number of antennas should be the same to the number of user terminals. And the user terminals can have either a single antenna or more antennas. Massive MIMO is differently a MIMO variant in which hundreds and thousands of antennas can be installed on a single base station, serving a number of user terminals using the same time and frequency resource, in which a single terminal can have a single antenna only, unlike the previous two cases. So one of the techniques to increase the spectral and energy efficiency of massive MIMO systems is employing those beamforming techniques. And therefore, we'll be dealing some three beamforming techniques here. And the first one is the analog beamforming, in which a single signal can be fed to a number of antennas, and so that different number of users can receive the same signal by the aid of phase shifters, which tilts the signal using time division duplex to focus the signal to the desired direction of the user. In the case of digital beamforming, different signals can be designed for different number of antennas, and so that the number of antennas will be associated to the number of radio frequency chain components, and so that as the number of antenna increases, the power consumption of the system also increases, and so that this system is differently known to have some power consumption problem. And some researchers have introduced to alleviate such problems by combining this analog and digital beamforming, which is what we call the hybrid beamforming. So in hybrid beamforming, only few number of radio frequency chain components are employed just by connecting the digital beamforming and the analog beamforming together, and so that the energy efficiency of the system can be achieved at the cost of some capacity due to less number of radio frequency chain components to be employed at a time. So as the number of antennas increase in such massive MIMO systems, so the energy efficiency of the system or the power consumption of the system also increase, and the energy efficiency will be degraded to some level. So our main objective is to achieve some energy and spectral efficiency of downlink massive MIMO systems by working on the power control of the system without minimizing those radio frequency chain components on the number of antennas. So to achieve the main objective, we will be going through some small objectives. That's to evaluate SNR after quantized DAC. Next is to compute bit resolution and combine with quantized DAC, and also we will be evaluating the sum rate of the system by working on those DAC resolution by minimizing the number of bits among those randomly generated bits, and so that the energy efficiency of the system will be calculated from perspective of the total capacity and the total power consumption. So related to this work, we have gone through some research topics under research number 3. The authors have evaluated the energy efficiency of the system by controlling the power of those phase shifters and power amplifiers, and still the gap which was observed on this area is that the researchers didn't address how this power consumption of each components can be evaluated, except just by putting some fixed values for each. Under reference number 4 to 8, the researchers still addressed the way how to enhance the energy efficiency by just employing some few number of components by compromising the capacity of the system while increasing the energy efficiency only. And again, under reference number 6 to 11, the authors still try to enhance energy efficiency by considering the successive interference cancellation as a detection, and without just considering how this successive interference cancellation creates the complexity during detection. So to alleviate the existing problems, we have gone through different techniques just by employing our own algorithm, and we have initialized some parameters like the range of the cell, some operating frequency, and the total transmit power of a base station. And based on these parameters, we have calculated the path loss, the maximum path loss as the cell age. And again, we have found the minimum received power of the cell age distance, so that the capacity of threshold capacity as cell age can be calculated on the basis of this minimum SNR and received signal. And again, after finding this threshold capacity, we have considered some randomly generated bits, and therefore we have calculated the capacity depending on these randomly generated bits, so that this capacity of randomly generated bits will be evaluated with the threshold capacity as the cell age. So if this capacity is less than the threshold value, then we consider some energy enhancing or capacity enhancing techniques like modulation techniques and coding schemes. And in this case, we have considered the coding techniques. And if this capacity is greater than the threshold value, then we don't need any wastage, and therefore we can minimize the number of bits until it reaches to the minimum threshold value. So as the number of bits iteratively decreases, the power consumption of the DAC also decreases, and so that we can evaluate the energy efficiency as decreasing number of bits can affect the power consumption of the DAC and the capacity of the DAC, even though the effect of the bit on total power consumption increases the effect of the bit on the capacity, and so that the energy efficiency will be enhanced through this technique. So based on our introduced algorithm, we have evaluated, or we have found different results. The first one is the relationship between the distortion of the signal and the number of symbols. It's obviously true that as the number of bits increases, the number of symbols also increase, and increasing bit number of bit mean leads to the increase in signal intensity, and that means as the intensity of the signal increases, the distortion level of the signal becomes to the lower level. And again, we have evaluated the relationship between the number of symbols and the quantization level, and we have found that as the number of symbols increase, the quantization level also increases, as the quantization is inversely proportional to the distortion and directly proportional to the number of bits and the symbols. Here we have evaluated the total power consumption of the system from perspective of the number of antennas in general. As the number of antennas increases, the total power consumption of the system also increases. And again, we have considered the total power consumption of the DAC by decreasing the number of bits within the DAC by using the principle of resolution, and so that we have found that the system with DAC resolution introduces less power consumption than the system without DAC resolution. And again, we have evaluated the energy efficiency with number of antennas, and found that as the number of antenna increases, the energy efficiency also increases to some level of number of antennas, and the graph of energy efficiency starts declining due to the effect of number of antennas on the total power consumption exceeds the effect on the capacity. The same to the previous case, the number of antenna is directly affects the energy efficiency of the system, even though we have been considering here the energy efficiency with the different number of users for a fixed number of antenna. So increasing number of user terminals still leads to increase in energy efficiency of the system for a fixed number of antennas, since increasing number of user terminals can increase the throughput of or capacity within a given area. Here also we have evaluated the relationship between the energy efficiency of the system and spectral efficiency of the system with their trade-off relationships. So as the number of user terminals increases, the spectral efficiency and the energy efficiency both increase together, and for lesser number of users, the spectral efficiency and the energy efficiency will be lesser compared to with large number of users. But if you consider the trade-off between the energy efficiency, while the spectral efficiency increase for some number of users, I mean, if while the energy efficiency increases for some number of antennas, at some point the energy efficiency, the spectral efficiency of the system starts declining. This means For some number of users only, or users and number of antennas, the energy efficiency and the spectral efficiency grow together, and while one increases, the other decreases due to the trade-off between the two. So in conclusion, distortion and quantization levels have been evaluated with number of symbols, total power, spectral efficiency, and energy efficiency have been evaluated with different number of antennas. And we have also evaluated the energy efficiency of dark resolution and its power consumption. And finally, we have evaluated the energy efficiency of the overall massive MIMO systems by considering low resolution dark. Thank you very much.